Okay, so welcome back to the Oxford Discrete Maths and Probability Seminar. So before we get going, maybe I'll just mention there are special events coming up the next 2 weeks. So next week we have a random matrix theory and combinatorics special afternoon, which we're organizing jointly with the random matrix theory group in Oxford. We've got Konstantin Tikhomirov and Gerard Ben Aruz. And then the week after, there's a very special event. There's a round-the-world relay in combinatorics that's happening at sort of 22 different locations around the world. So there are seminars, enough seminars to satisfy anybody, I hope. So it's 22 hours of consecutive hours of seminars. You can find all the details on the webpage. We have Jacob Fox talking, but there are lots of other wonderful people talking in lots of different locations. As usual, there'll be Zoom details on the webpage close to the event. Okay, having covered all that, back to this week. So it's a great pleasure to have as our second speaker today, Michael Krivelevich, who's going to talk on cycle lengths in sparse random graphs. Thanks.
Okay, thank you, Alex and Christina, for your invitation. You can hear me, yes? Okay, great. So what I'll be talking is cycles, or rather cycle lengths in sparse random graphs, and this is a joint work with my two collaborators. The first of them is Yahav Alon, who is a PhD student in Tel Aviv, under my supervision. I don't think he's a relative of Alon, in case you wonder, but he's a good guy. And the other co-author is Eyal Lubetzky from Current Institute at NY. Very good. So, okay, let me describe you first the general setting. So we'll be talking about cycles and about random graphs. Of course, by random graph, I mean mostly, but not solely. I will discuss some different models later. So, but mostly we'll be talking about the so-called binomial random graphs, which is denoted by G and P and defined as usual as follows. We have a set of n labeled vertices 1 up to n, and every pair ij is an edge of the graph, independent with probability p, where p might depend on n, and these choices are done independently. And the graph theoretic parameter, or rather the graph theoretic entity we'll be discussing, is denoted in this talk by script L of G, and script L of G is a set of an n vertex graph G. L of G is a set of all integers L between 3 and n, such that G contains a cycle of length L. So as a rule, we forbid loops and multiple edges, which means we don't have cycles of length 1 and 2, and therefore every cycle length is somewhere between 3 and n, and we would like to understand which cycle length we typically have in our random graph GNP. So that's a question, or rather a meta question we'll be discussing. So in general, this juxtaposition of random graphs and cycle lengths is very, very natural, and you can expect that a substantial amount of work has been devoted to this problem, and it's indeed the case, and I will mention some of the previous chapter results, but still turns out there's some stuff to be done and to understand in this thing. Okay, let me start by simple things. And by simple, I mean we theoretically are interested in the whole range between 3 and n. Let's look first at its upper and lower ends. For the lower end, when k is a constant, let me denote by x sub k the random variable counting k cycles, or rather the number of k cycles in GNP. And then its expectation can be easily written down, and it's of the order n to the k, take p to the k. Which means that if your p is larger than 1 over n, then we expect many cycles to appear. And we can as well compute the variance. The variance is given by this expression. You don't really need to dwell into it deeply, but you can figure out that in the case where n p tends to infinity, expectation tends to infinity, and variance is not that large. Namely, variance is the little law of the expectation squared. And then by using the so-called second moment method, or Chebyshev's inequality, we can derive the probability of x being equal to 0 is at most the variance of x divided by expectation of x squared. And this ratio is literal of 1, which means with probability tending to 1, we have a cycle of length k. The notation we will be using during this talk is with high probability, which I will abbreviate by WHP. So with WHP, we have a cycle of length k inside, and actually we can aggregate, and if as long as k is fixed, we have a whole interval between 3 and k inside the set of cycles in our graph. So on one hand, we're doing quite well. So let's look now on the other hand. And the other hand, the first question that comes to mind is when exactly we have n as a cycle length in our graph. In other words, when exactly our graph is typically Hamiltonian. A Hamilton cycle in the graph is a cycle through all of its vertices, and the graph is called Hamiltonian if it contains a Hamilton cycle. And then this a very, very classical result by convolution, similarity, and independently by Bolover from ACES, which says as follows: if the probability P of n satisfies NP minus log n minus log n tends to plus infinity, all logs in this talk are natural logs. So if the expected degree in P is tiny bit larger than log n plus log n, then with high probability what we get is a Hamiltonian graph. Which means in our terms with high probability n belongs to a set of cycles in our graph. There is an easier part of this statement, which is much easier to prove, and it still needs to be said. So if NP is tiny bit smaller than log n plus log n, which means if NP minus log n tends to minus infinity, then with high probability we have vertices with degrees less than 2. And of course, once you have a vertex of degrees less than 2, then you cannot have to get Hamilton cycle, because for any cycle to pass through the vertex better have a degree at least. So in this range, we are not Hamiltonian. So in fact, we now understand more or less what happens for the lower and upper end of the spectrum, of the possible spectrum. And in fact, we can go even higher and we can talk about the so-called pancyclicity. So let me define this notion for you. Suppose we have an n-vertex graph. We call this graph pancyclic if you have all possible lengths. So as I said before, we don't have loops, and therefore 1 is not cycle length. We don't have multiple edges, and therefore 2 is not cycle length. So the best we can hope for is to get every cycle length between 3 and n. And if this happens indeed, this graph is called pancyclic. And then there is a theorem of Cooper and Fries from 1990, which goes as follows. The probability of GNP being pancyclic, it goes from being nearly 0 to nearly 1, exactly at the point of infinity, namely if NP minus log n tends to minus infinity, then with high probability your graph is not pancyclic, whereas if NP minus log n tends to plus infinity, then your graph is actually not Hamiltonian, but pancyclic. So the moral of this theorem is basically the bottleneck for pancyclicity is Hamiltonicity. Once you get Hamilton cycle, you are very likely to get not just length n, not just small lengths, but actually all lengths between 3 and 10. So that's the result. Now let me indicate its proof to you, and what I will be proving, or what will be indicating, is not the original proof, but the proof actually using our approach, because it will be nice and instructive to see how our approach can be used for this type of statement. So zero statement first. Zero statement is proving that you are not pancyclic when your probability is not high enough, and that's immediate because of in light of the Hamiltonicity. If you don't have Hamilton cycles, then n is outside your set of cycle lengths, and you are not Hamiltonian. So much more interesting is, of course, and much more meaningful is, of course, a one statement. And that's what I'm going to sketch you. And the sketch is not the original proof, but rather something different. Okay? And it's helpful to see it to demonstrate the voltage. Now, what we'll be using in this proof in many places in this talk is a so-called double exposure. And it's the following fairly useful and fairly simple fact, which goes like this. So suppose you have 3 edge probabilities, P1, P2, and P. And you look at serial random graphs. The one of them is GNP. And the other 2 are independently generated GNP1 and GNP2. And then the claim is that if you take the union of GNP1 and GNP2, you get exactly, not approximately, you get exactly the same edge distribution as GNP. And that's very easy to see because on both sides of this comparison, you get a product probability space. Each pair appears as an edge independently. For GNP, the probability of IJ of being a non-edge is 1 minus P. For GNP1 union GNP2, you should fail in 2 independent experiments. And the probability of failing is 1 minus P1 times 1 minus P2, and therefore you get the same probability for every factor P, which means you get exactly the same distribution. Now, sometimes it's a very neat trick and very simple, but very neat. So sometimes it's also called sprinkling, because in very many instances, actually most of the probability mass goes into P1. So you create the main structure inside GNP1, and then you use GNP2 to complement what you need to complement, and we'll be using this trick here. So if you solve this equation here for P1 and P2 and P, you can see that P1 plus P2 is at least. Okay, so let me explain your indicator the proof for pancyclicity. As the way as we view it, so we should handle triangles separately for some technical reason, but that's not very hard. For triangles, you can use the second moment, or you can use again double exposure to show that in this range of P with high probability you do have a triangle. Triangles are not a problem here. So let's look at the range from 4 to n, and let's prove that with high probability, the whole range from 4 to n falls inside your set of cycle lengths. And for this, it suffices to prove the following statement. You fix your L. L is anywhere between 4 and roughly n over 2. And you would like to look at the pair of cycle lengths, which for a reason I will explain in a minute, go together. And you would like to look at cycle lengths L and n minus L plus 4. And you ask what the probability that one of them is not a cycle length in your graph. And if you know to prove that this happens with probability, this is fairly small. And fairly small in this case means a exponential L times some function tending to infinity, arbitrary slow, but tending to infinity, this omega n. Then you can use the union bound over all possible cycle lengths, and you can see easily that with high probability gets the full interval for n inside the set of cycle lengths. So let's look at our H probability P. We take it to satisfy NP minus log n minus log log n. Let me denote this quantity by f of n. And we have G drawn from GNP, and vertex set is usually 1 to 2. So we use double exposure. So G is the union of G1 and G2, and the probabilities here are not equal. We put most of the H probability into P1. So P2 is rather tiny. P2 is Fn divided by 2n. But the nice feature of infinity is infinity divided by 2 is still infinity, which means P2 is still something super linear. And P1 is still large enough. We chop off a tiny piece from P to get P1. But P1 is large enough to deliver you Hamiltonicity. So G and P1 is still typically Hamiltonian. So you expose G and P1 first. You get a Hamilton cycle C sub n. And without loss of generality, since we have 2 independent copies, you can assume as well that Cn is a cycle 1, 2, 3, etc. up to n and then 1 again. So we get a Hamilton cycle in the first graph, and then we need to complement it in the second graph to get every possible length. Okay, so let's look at some particular length L, or rather some particular pair of lengths L and n minus L plus 4. And suppose we are so lucky that for some 3 values I, J, and K, where I and J are any integers between 1 and n, they are not equal, and K is at most L, technically it's at most L minus 3. Suppose we are so lucky to get 2 edges Ij and I plus K, J plus L minus K main to near graph. Then we're in a good shape, because what we can do, we can take 2 short arcs of the Hamilton cycle to get a cycle of length exactly L. And we can also take 2 long arcs of your Hamilton cycle to get a cycle of length exactly n minus L plus 2. Which means if we get this pair of 2 green edges, then we are in good shape and we can deliver both cycle lengths L and cycle lengths n minus L plus 2. Which means it's enough for us to guarantee that with high probabilities, with very high probabilities we need it to happen, we have a pair of green edges of this. Now let's do some simple counting. Altogether, there are n squared or order n squared times L options for Ij and K. So Ij is anywhere, and K, if we take Ij, so for K, we can shift it in this way. I plus 1, I plus 2, etc., all the way up to I plus L minus 3. So altogether, there are n squared L ways, order n squared L ways to choose I, J, and K. And therefore, For each such wave, we need a pair. A pair happens in the second graph is probability p2 squared. The pair does not happen in the second graph is probability 1 minus p2 squared. Altogether, we have n squared L pairs. And therefore, we can expect that the probability that none of the pairs appears is 1 minus p2 squared raised to the power of the number of options. The number of options was of order n squared L. And then by substituting the value of p, we'll see that what we get is of order exponential, and the exponent is negative, of course, minus omega of n times L. And then we need to aggregate. I am cheating you a bit, of course, because there is a small red asterisk here, and we need to take care of dependencies. There are some dependencies here, so we need to be careful a bit and need to take care of them. So let me explain you briefly how we can take care of them. So we need to overcome some possible dependencies, and then in order to overcome them, we use double exposure again. So we take the second random graph G and P2, and we split it into two graphs G3 and G4 of roughly equal probability. So suppose we are able to put an Hij inside of our graph, then this Hij brings along a lot of potentially useful edges, and they are written here. They are of the form I plus k, j plus a minus k minus 2 for k anywhere between 1 and l minus 3. And then we expose, let's say, G2 as a union of a red graph G3 and the purple graph G4, which have the same distribution, but they're independent. And we will be creating sets, we will be creating edges Ij in G3, and we will be creating a potential ways to close these edges, which are given by Sij in the second random graph. And our goal will be to prove that if we look at all edges falling inside the third graph G3, and if you look at the corresponding sets Sij, their union is substantial. Substantial means what is more or less dictated by expectation, namely n squared times p2 times l. And the way to do it is as follows. If we take the first potential Hij, and suppose this H we expose it, we flip a coin for Hij. Most of the time it's not an H, but if you're lucky enough, it happens to be an H, and this H delivers alone a full set of purple edges Sij. But if you're so lucky now, instead of taking and exposing arbitrary next pair, what we do, we go to the potential pair Ij, whose purple edges are disjoint from the already obtained purple edges, and simple count shows you that there are many such edges, and therefore you expose the next pair, and if you're so lucky, you get the next portion of purple edges, and this way you continue until you get enough edges, okay? And then you can easily prove, it's actually not so hard in arguments, you can easily prove that with very high probability, you indeed get of order n squared p2 times l edges in the union of Sijs. Now we go to the second graph. Second graph, or rather fourth graph G4, is independent of the previous ones, and we go edge by edge. And the probability is that for now we need just one purple edge to happen. And the probability there is no useful edge is 1 minus p2 to the number of potential useful edges. And we only need one purple edge, and we get it with very, very high probability. The probability there is no useful edge is exponential, is omega of n times n. And once we get this purple edge combined with the corresponding red edge, you get what you need. You get two cycle lengths, L and n minus L plus 2. So this would be the idea. Okay? So that's kind of simple approach. There's some technicalities beyond this thing, but in a way, it's not that hard to do. So actually, what we proved is the following statement. We draw G from GNP. NP is a bit more than log n plus log n. The difference, not the ratio, the difference between NP and log n minus log plus log n. Tends to plus infinity, then we get is not only Hamiltonian graph, but it also what's sometimes called two-pancyclic graph. So I need to give a definition of that's the result of Colin Cooper from 91. So I need to give a definition of a k-pancyclic graph. So a k-pancyclic graph is a graph on n vertices, say, which has a Hamilton cycle C, so that for every other cycle length between 3 and n, we have a cycle of this length, which is not drastically different from our base Hamilton cycle. You need to add k edges at most to get the cycle length. So if we go back to our previous statement, in order to get a cycle of length L, We basically used most of the edges coming from the Hamilton cycle, which fixed one and for all, and we needed only 2 edges to create a cycle of length L, and therefore we created typically a 2 pancyclic graph. Actually, this is a modular result of the same Cohen Cooper, and he proved that actually the threshold for Hamiltonicity is exactly the same as the threshold for one pancyclicity. So at the threshold, once you are beyond the threshold for pancyclicity, for Hamiltonicity, not only you can find the Hamilton cycle, not only you can find every cycle length, you can actually find one Hamilton cycle and one additional edge for every cycle length, so that you have one pancyclic. Good. Now we understand situations for NP, which is around log n. There is no need to go beyond it because we already have what we need to have, and then we can go actually lower and we can ask what happens for smaller values of p. For smaller values of p, we have this very nice result of Thomas Schuchik from 30 years ago, and it goes like this. So if we take p satisfying NP tends to infinity, the expected degree of the graph tends to infinity. We draw G from GNP, and now we can no longer expect to have a Hamilton cycle. And actually, we are bound to lose some vertices. Now, how many vertices we are bound to lose? Every vertex of degree 0 or 1 is lost. And therefore, it might be a good idea to count them. So let me note by n at most 1, the number of vertices whose degree is 0 or 1. This is our guaranteed loss, and we are happy if we are not losing much beyond this. And the result of Thomas is indeed such. Then for every positive epsilon with high probability, we have the following interval inside L of G. It starts at 3, so we are very fine at the lower end. And it goes all the way basically where it can go. Instead of stopping at n minus n at most 1, it stops at n minus 1 plus epsilon n at most 1. Okay? So we are more or less as good as we can hope to be. And this can be proved in the same spirit as Pancyclicity. In a way, I could have said that Wojciech borrows something from us, but of course, historically, it was the other way around. We did borrow some ideas from Thomas. And if we are to implement something like this, the idea would be, if we go back to our original proof, we need to find a long cycle first, and then we use some kind of sprinkling to complement it to all cycle lengths. And for this, we need some result about long cycle lengths, and this is the result by Alon, which is in even earlier result. It's from 86, actually. A funny deal is when I was preparing to this talk, I realized very clearly that a field of random graphs has come out of age, because there's a lot of results here which are probably older than a good half or maybe even more of participants of this seminar. Some quite venerable results, or some quite young people, I would say. So the result of Fries from 86, which is 35-year-old, you can compare your age to this result. You don't need to report to me your findings. And it goes like this. You take NP tending to infinity, so the expected V tends to infinity. You draw G from GNP, you count useless vertices, which are vertices whose degree is 0 and 1, and then turns out there is a cycle doing nearly all the job for you. There is a cycle as long as n minus a tiny bit more than n at most 1. So there is a cycle of length n minus 1 plus epsilon times n at most 1. Actually, the result of Fries, it's even better, because his result goes as follows. You can take U and P to be as large as some constant C, where C should be large enough as a function of epsilon. Okay? So you're doing quite well, and then the idea would be you take this cycle as a basis, and then you expose G into parts. First, you find a long cycle in one part, and then you use helpful edges relative to this cycle to complete to all cycle lengths in the result. So this would be the idea to reprove the result of Wojciech from 90. Very good. So let's go even further. And what happens if NP is of order bigger or 4? Which means what happens if the expected degree is a constant? Now, you can go low, but there is a limit to how low you can go. And you should probably stop at NP, which is a bit above 1, because otherwise what you get is so-called critical, even subcritical random graph. And for the critical or subcritical case, all components are pretty small. They are polynomially small, or they are even logarithmically small, which means you cannot hope to get that many cycles or that many long cycles, and therefore, basically, if you want to prove some meaningful results, you better stop and start actually action in supercritical action. So let's assume that NP is at least as large as 1 epsilon for some constant epsilon. Okay. Now, still, we are bound to lose quite some stuff. There are many cycle lengths we can no longer expect to appear. And let's look, in order to figure out this, let's look at the lower range and the upper range. For the first, for the lower range, if you look at the constant k, and if you see it's constant, then what happens is, as a result of Bolobash and intended by Karolinsky and Ruchinsky from 81, the number of cycles of length k in G and C of n for any value of C, whether above 1 or below 1, you don't expect that many cycles. The expectation is constant. Actually, a good intuition says that if something has a constant expectation, then you can expect the distribution to tend to Poisson distribution. And that's indeed the case. So you get a Poisson distribution, meaning in particular that the probability of not having any cycle of length k is bounded away from 0. And not only that, actually, you can prove the probability of not having any cycle between 3 and k is bounded away from 0. So in this sense, we cannot guarantee cycles of short length. Okay. Also, we have a problem of a different kind. We have isolated forces, have actually pretty many of them, a linear number of them typically. And also, especially if your NP is quite close to 1, above 1, but still not much above 1, we are limited by the size of the largest connected component. And the size of the largest component is typically linear, but fairly small if epsilon is fairly small, which means we don't expect much. So in some sense, we are squeezed between cycle lengths, which are super constant on one hand, and linear on the other hand, where the proportionality constant might and should depend on epsilon. Okay, as a side remark, let me mention the following deterministic approach to prove many cycle lengths, actually a full interval of cycle lengths, and it goes through the so-called definition of beta graph. It's not very standard definition, but it's quite handy. So suppose we have a constant beta, and we are looking at an L-vertex graph. So let me call this graph a beta graph if the following holds. You take any two subsets A and B of vertices of cardinality at least beta n, and you postulate that there is at least one H of G between A and B. So this is some kind of connectivity or expansion notion. It's not exactly expansion because you allow for isolated vertices. It's not exactly connectivity, but it's some kind of illustration of connectivity. There is an edge between every two large pieces. It's actually quite easy to prove that if you draw your random graph G from probability distribution G and C of n, then with high probability what we get is a beta graph for an appropriate beta, and actually beta is roughly inversely linear in C. So it's quite easy to prove, to verify that a random graph G and C of n for large enough constant C is beta graph. And then you can use the following deterministic statement as opposed to random statement by Lemore, Friedman, and myself from 2021. It has been published quite recently. So you take your beta to be some small enough constant, but it's not ridiculously small. And then there are two constants, B1 and B2, depending on beta. We are probably more interested in the upper range. In the upper range, beta 2 is of order linear in beta. And then if you take any beta graph on vertices generated randomly or not, that's a deterministic statement. What you get is a full interval starting at B1 log n and ending very close to it. So deterministic, that's a very nice and handy tool for proving many cycle lengths in such a graph. This result is optimal in many senses because there are very nice expanders of logarithmic girth, which means we cannot really hope to get a cycle shorter than logarithmic. And also in such a graph, if, for example, if you take a random graph, you have linear many vertices. You might have linear many vertices which are isolated, and therefore we should stop short of n. We should give some distance linear n till we reach n. So this in particular implies, if you apply it to random graphs, this implies immediately that if your C is a large enough constant, you get an interval of length linear n. And not only that, you get an interval which covers nearly everything as your C grows larger and larger. But still, we'd like to be even more precise, and we still want to say some even more accurate statements. And let me formulate the first result, and it goes like this. There is some constant C naught, which we don't calculate, we just postulate it exists, that's such that for almost every C, for almost every should be interpreted here, for all C but a set of measure 0. So for almost every C, quite unfortunate, I don't see Oliver smiling, for almost every C in this range, if we draw G from G and C over N, then for every epsilon, and for any sequence tending to infinity, we stay away from constant interval, we stay away from the maximal length, but we do get an interval starting at omega n and going all the way to maximal cycle length. So not only we get maximal cycle length, but we get a full interval starting from omega of n and nearly all the way. So nearly all interval up to L of G, maximum L of G is filled with cycle length. So in the lower range, is this possible because we do need to exclude cycles of short length. For the upper range, we are doing quite well because we are basically approaching the cycle length nearly fully. We are losing essentially little of length. Now, in order to apply the statements, there are one missing piece and one caveat here. So for the missing piece, we need to be able to say something intelligent about the circumference of a graph, which is its longest cycle. And we know quite some things. I actually mentioned some of them, and I will mention some of them soon, some additional soon. And there's also this red and a bit annoying almost every, which unfortunately we cannot quite circumvent, and I will explain this soon why it's there. But still, we are doing reasonably well, and we can actually say some intelligent things for every value of C. Okay, so let me explain you the proof of Theorem 1. So the proof goes quite similar to our proof of pancyclicity. So we need to prove first the following main lemma. And the lemma, the idea to approach it would be first to get a long cycle and then to drop some more randomness and small number of random edges on top of this long cycle to get a full interval. And the lemma goes as follows. We fix any value of delta, so delta can be arbitrarily small. We take a cycle of length n, and we drop a random graph g and delta of n on top of this Hamilton cycle. So which means we drop something like delta n or delta n of 2, if you wish, random edges on top of a Hamilton cycle. And then the claim is that no matter how small is delta, and no matter which function omega of n you take, as long as omega of n tends to infinity, then we get a full interval between omega of n and n minus 1. And actually, you know the proof, because actually what we did in the argument I showed you is exactly the same. What we did is we started with the cycle first, and on top of this cycle, we drop some randomness. We drop some random edges to get the full interval. But unlike in the previous statement, beforehand, we assumed that NP tends to infinity, and therefore we were able to prove to get all cycle lengths between 4 and n. Now we do not longer assume that NP tends to infinity. NP actually can be a small constant, and therefore we need to give up on cycle lengths which are short, and we need also to give up at least technically on cycle lengths which are quite close to n, but otherwise we are doing quite well. Okay, but for this we need to apply some knowledge about a long cycle, and it's given by the following a refined result by Michalis and Nastas and Alon in 21. And what they proved is the following. They proved the existence of a monotone non-decreasing function f, and the constant C naught such that if you look at G and C over n, and if your C is larger than C naught, then if you take the so-called scaling limit, you take the maximum cycle length or the circumference of your graph, and you normalize it by n, you get some constants. It turns out that in probability, this quantity approaches FC, which means for this particular function FC, they were able to define in some sense to calculate the cycle length approaches f of c. Now, in principle, they defined a way to compute this function fc up to any degree of precision, but that's not an explicit expression. And in particular, quite unfortunately for us, they weren't able to argue that f is a continuous function. And therefore, what follows from their proof, and actually a trivial consequence is this function is monotone, non-decreasing, which is quite natural, of course. The more edges you put on your graph, the more likely you get a longer and longer cycle. Okay, and now back to our proof. We take G, we expose it as G1 and G2, and you need to give away from the green graph G. So for the green graph G, the probability is not C of n, but rather C minus delta of n. And then you complement it by the blue graph. The blue graph is distributed like G and delta of n. Now, with high probability, by the statement of Anastas and Fries, you get a cycle C in the first graph of length, which is quite close to FC, but F not in point C, but rather in point FC minus delta minus little of n. And now we apply the main lemma on this long cycle plus the randomness we have left in the blue graph to get the full interval between omega of n and F in the point C minus delta n minus omega of n. So we're doing quite well, and the only thing left to argue is to take our delta small enough so that F of C minus delta is larger than, is very close to F of C. Well, that's a problem, because actually, in order to argue this, we need to argue that C is a continuity point of F. And we cannot quite guarantee it, and therefore, instead of getting it in each and every point C, we can only claim it in the continuity point of F of C and most of the point as such, but not every point of such. It would be really ridiculous to see that F of C is not continuous, but unfortunately, we cannot. But still, we get something for each and every value of C. Very good. So let me talk about some extensions of Theorem 1. So basically, Theorem 1 is more of a machinery than a result, and let's see how we can apply this machinery. What we actually proved is the following statement. So suppose we have some high probability lower bound on cycle lengths in a random graph G and C of n. Let me denote it by function BCN. Then if we have this machinery BCN, then we know that for every value of C and for every value of delta, if we look at the random graph G and C of n, then we get typically every cycle length between omega of n and B, but not in point C, but B in point C minus delta. So we have all cycle lengths between omega of n and B in the point C minus delta n. Well, technically, we subtract omega of n, we don't have to do it. So we have all cycle lengths. So in particular, for any value of C, if you have some combinatorial, some other way to argue about a long cycle in this random graph, then by applying this argument, you get some meaningful statement about set of cycle lengths. You, in particular, get a linear long interval inside your set of cycle lengths. In particular, in this very interesting supercritical regime, if you take your C to be 1 plus epsilon, and if epsilon is small enough, you are in the supercritical regime, then we know that we have a linear cycle, a cycle of linear lengths, that is the classical result of Eyal same for 81. Actually, we know that the dependence on epsilon is epsilon squared, which is optimal. And actually, we know even the precedent constant, we have a cycle of lengths at least for third epsilon squared. Actually, as a side remark, let me mention that one of the very nice problems left about supercritical graphs is to figure out what's a typical length of the longest cycle in supercritical graph. It's not to be linear n, it's not to be of the order epsilon squared n, it's not to be actually between 4/3 epsilon squared n and 2 epsilon squared n, but we don't know the right constant. We know that the constant is not 4/3. We know that the constant is not 2, and it would be actually very nice to put this constant close together, even to merge this interval to one point, but we don't know to do it. But still, we know that for any epsilon greater than 0, there is a cycle of length at least for third epsilon n. And then we can use this as a function BCN. And then we can argue that for every gamma which is less than 4/3, we have a full interval between omega of n and gamma epsilon squared n as an interval of cycle lengths in our graph. So not only we get one cycle of linear lengths, not only get one cycle of lengths proportional to epsilon squared n, we actually get a full interval starting at omega n at any super constant length and going all the way to something which is at least as large as 4/3 epsilon squared. So that's quite nice. Now, another observation I would say is whatever we said about undirected graphs is valid for directed graphs as well. We can apply it to the model of random directed graphs, which is usually denoted by DNP. So DNP is a random directed graph, which is defined as follows. The circumference is 1 up to n. Now you take every order pair ij. I is no longer less than j. So in principle, you can have an hij and ji. You flip a coin for every hij with probability p. It gives an h, and this probability minus p gives a non-h, and that's how you get your random space. And then you can ask the same questions: how long is the longest cycle? Do you get all cycle lengths, etc., etc., etc. And the idea to do it is as follows: you first get a long cycle, a Hamiltonian cycle, a cycle which is along an n, and that you will be efficient for these two additional green edges, an edge, a directed edge going from j to I, and a directed edge going from I plus k to j minus L plus k plus 2. Now, once you get these two edges, what you get, you are taking our short arcs of this long cycle, and you get a cycle of length L. And as opposed to the undirected case, here actually you can allow your L to be as large as n, and the way to get all cycles, instead of getting them in pairs, you get a direct cycle of length L for every L between something 3 or 4 or omega n and all the way to n. But basically applies the same idea. Now, another possible application is to the quite popular recently model of randomly perturbed graphs, and it goes like this. It's some kind of juxtaposition of a deterministic and random graph. You take a deterministic graph possessing some basic property, you put on it some little randomness, and you say that this little randomness is enough to fix otherwise adverse properties of this random graph. Specifically talking about cycles, we need the following result of Daniel Reichman, Wojtek Samot, and myself about trees and cycles in perturbed trees. And it goes like this. So we start with the tree and vertices. The only thing we need to assume about tree is it has bounded degrees. That's important because otherwise it's not. So you have a bounded degree tree, or if you wish, you have a connected graph, and you know that in this connected graph, you have a tree of bounded degree. For example, if you start with a bounded degree connected graph, of course, you have such a tree. And you take any constant delta, and you put a random graph G and delta of n on top of your tree. You start with a deterministic tree. The only thing you assume about your tree is that it has bounded degree, and you put something like delta n random edges on top of your graph. And delta can be much smaller than 1. So the random graph is very, very far from being supercritical. You don't expect any cycles, you don't expect much cycles, etc., etc., etc. And yet it turns out that if you put a random graph on top of your tree, you get a fairly long cycle. Specifically, you get a cycle of length at least c, and for c, which is a function of big delta and small delta, and c is a positive. And now, if we given this, then we can apply this in 2 steps. We first get a long cycle, and then we use another bunch of randomness to get all cycle lengths. And what you get eventually is the following result. We start with a tree on vertices of bounded maximum degree. On top of this tree, you put a random graph G and delta of n for any value of delta. And then you get a full interval of length c, and for some c, which is a function of delta and delta only, inside L of G. So you start with a tree, no cycles whatsoever. You put on it a random graph which in itself contains very few cycles, if at all. And then putting these things together, you get actually many cycles. And the proof is basically apparent. The proof immediately follows from our machine. Very good. So let's move onward. And the next and the last random space I'm going to consider is a random space of random d-regular graphs. So a random d-regular graph, you fix 2 parameters n and z. Mostly we'll be talking about d, which is a constant. N goes to infinity. If you want to get a d-regular graph, you better require n times d to be even, because otherwise there is no such graph. So let's assume that nd is always even. Okay, and you take the probability space of all d-regular graph on n labeled vertices. You assign the same probability to every graph. That's a uniform probability space, and you like to research such graphs. Now you can start with d equals 1, which is a very prosaic probability space, just a perfect matching, not very interesting. You can make the next step and to take d equals 2. For d equals 2, you do get some cycles. It's basically random permutation, but you don't get that many cycles. And therefore, in terms of kind of interest, in terms of meaningful probability space, you better start it from d equals 3 and more. D equals 3 is already interesting enough. So let's assume that d is at least 3. Now let's see what we can expect there. So in some sense, G and D is quite similar to G and C over N for C, which is quite close to D. And therefore, in some senses, you can expect some cycles. In some sense, it's very different. For example, in G and C over N, we know for sure, well, not for sure, we know for almost sure that we have lots of isolated sources. And therefore, we cannot hope to get a Hamilton cycle. Now here, a priori, it's not necessarily the case because we are guaranteed 3 edges at every vertex. And not only this, there is a famous result by Robinson and Wormwood saying that for every fixed value of z, this high probability random deregular graph is Hamiltonian. So you get a cycle of flex n. There is no inherent obstacle for you on your way to Hamilton cycle. And indeed, that's not an easy statement. That's something which requires quite an effort to prove, but still it's true. You get a Hamilton cycle. On the other side of the interval, things haven't that improved. There is indeed similarity here between G and D and G and D of N, and that's a result by Bolobich and Wormwood, and independently by Wormwood. And they proved that if you look at the k cycles for a fixed k in G and Z, you don't get that much. You expect some of them, you don't expect many of them. The expectation actually tends to a constant. This constant is what I denote here by lambda decay. And they were able to prove that actually the random variable counts in k cycles in G and D has an limit a Poisson distribution. And as a result, with probability bounded away from 0, you don't get any cycle of length k. And actually, with probability bounded away from 0, which we can even write down explicitly, you don't expect any cycles of length up to k0. So we are still kind of pretty miserable, if I can say, at the lower end of the spectrum, and we do have some hope at the upper end of the spectrum. Let's see what we say. It turns out we are doing quite well. So for every integer d, we look at a random deregular graph, fixed d, and then for every sequence omega of n, once we stay away from the constant range, once we started at the super constant range, we get all cycle lengths between omega and n. So the result is you need to give up all constant lengths, but once it becomes super constant, you get it all the way from omega n up to n. And this is, of course, best possible. Now, let me explain you briefly how to prove it for d equals 3. And there is some kind of montanistic here, implied by contiguity, for example. Once you prove it for d equals 3, it applies the theorem for every d which is at least 3, assuming at least that n is even. And for n odd, you can do it. For n odd, you need to take ud to be even. And for n odd, there is separate proof starting at d equals 4, and then by so-called contiguity, you can extend it to d equals 6, etc., etc., but we won't do it here. Okay, how do we prove it for the case d equals 3? Now, we split it into two cases, the interval from omega of n by up to n minus omega of n, and the proof here is quite similar to GNP. For GNP, what we did to remind is the following. We first got a long cycle, and then on top of this long cycle, we put some additional randomness to get all cycle lengths. Now here we need some tool which would allow you to split the randomness in a random circular graph into two pieces. And luckily for us, there is such a tool which is called contiguity, and it goes like this. You take any monotone graph property, and then it turns out that the probability of having this monotone graph property with probability tending to 1 is GN3 is if it tends to 1 in GNP, this happens if and only if you look at the following probability space. You take a Hamilton cycle, Cn, and you put on top of it a random graph GN1, which is nothing else but a random matching. So in words, we know that a random irregular graph is contiguous to a union. Formally, we need to declare this joint union is contiguous to this joint union of Hamilton cycle and a random perfect matching. On both sides of this comparison, you get a three regular graph, and it turns out that's a very non-trivial statement. It turns out that you can operate with one of them to derive result for the other, and luckily for us, the probability space of a Hamilton cycle plus a random matching is good enough for us because we have two separate systems of randomness, and then we can expose them one after another. So what we need is to prove that for any value of A in the interval between omega of n and roughly n2, if you take a random perfect matching on M, we will have two edges of the form ij and I plus k, j plus a minus k minus 2 for some value of k with probability which is exponentially close to 1. And this is true, and the argument is a bit more complicated than the argument for random graphs, but it still works. That's how we handle the major interval from omega of n to n minus omega of n. We still need to cover this minor interval in the variant. And the way to do it is to use the following theorem, another theorem by Robinson and Wormald, the same Robinson and Wormald, by another result, minor of 1. And what they proved is the following thing. Look at G and Z. You can think about a random three regular graphs. Let's say D is equal to 3, and you have some two extra parameters, M1 and M2. Both of them are negligible compared to square root n. And then what you do is the following experiment. You draw a graph from G and Z, you draw a random graph from G and Z, you draw a random set E1 of edges from the graph, you draw a random set E2 of non-edges, of edges from the graph as well. And then we are looking for a Hamilton cycle. We know it exists, but now we need something more delicate. We need a Hamilton cycle which does include all edges of E1 and which does not include any edge in E2. And according to their statement, not only our graph is Hamiltonian, but there is a Hamilton cycle avoiding a random set of size M1 and of size M2 and including a random set of size M1. And this statement can be used to prove what we need for the lower range. And let me briefly, towards the end of this talk, I'll try to be brief to explain how to do it for this range. So let's assume that L is even. The case of odd n can be treated similarly. So take G drawn from G in 3, and we pick k random edges. U1, V1, UK, VK. Now, this random edges, because L is fairly small, typically what you get is a match. So here's your matching. And now you look at this matching. The matching is between vertices UI, VI. Now, our graph is 3 regular, which means that every UI has x, y, yi as its neighbors, and every vi has xi prime, yi prime as its neighbors, and what you get actually is separate sets of edges because you have very few short cycles. Okay, so that's the picture. And now what you're going to do, you are going to delete the vertices u1, v1, etc. to uk, vk, and you are going to, by deleting these vertices, you delete also edges incident to them, and then what you get is a graph. All of whose degrees are 3 apart from the degrees of x size and y's, and in order to compensate for it, you add these blue edges here. So altogether what you get is a graph on n minus l edges. This graph is 3 regular, and with respect to this 3 regular graph, actually these blue edges are random. So you get a random 3 regular graph with n minus l vertices and a random set of l blue edges on top of it. And then by the result of Robinson and Wormald, there is a cycle, a Hamilton cycle in this smaller graph, avoiding this set of blue edges. And then you can lift this set, this Hamilton cycle to a cycle of length exactly n minus l in your graph. And this is, you can do it for each and every length, and this is your way to close the interval, which is quite close to n. And for a cycle which is of odd length, you do similar things. Let me just keep them here, but instead of deleting all these edges, you insist on retaining one of them and avoiding the rest of the edges. You can think it through quite easily, and that's your way to complete it. And that's how you complete the whole range. So to repeat it, for random 3 regular, random d regular graph in general, typically not only you are Hamiltonian, you have a full cycle range between omega of n for any omega of n, tending to infinity and n. Very good. So let me stop here. Thank you for your attention.
Great, thank you very much, Michael, for a very enjoyable talk. Lots and lots of good stuff in there. So if anyone would like to ask questions, please do ask in the chat or just unmute yourself and interrupt. Actually, maybe I could start by asking a couple of things. About your theorem 1, so when your edge probability is constant over n, back on page 14.
Mm-hmm. Mm-hmm. Okay.
Thank you. So at the top end of the range, so there's a sort of interval of linear length between what you can prove and the longest cycle. What do you think happens in that?
Well, my guess, I wouldn't bet a huge bet on it, but my guess actually that you would get a full interval up to maximum cycling.
Okay.
But we don't know to prove it, and there's actually a lot of delicate questions because we don't quite understand it. For example, it could be that maximal cycle is fragile. For example, you can ask whether there is typically a unique cycle of maximal length. We don't know to answer this question. So it's a bit shaky, but but once you kind of stay away enough from this length, and then we are on a safer ground, then we can prove it.
Okay, and the other thing I wanted to ask was, so in the proof you were doing this double exposure where you drop by delta and then threw the edges back in again. Mm-hmm. So I'm just wondering, so here I mean, for up to linear length, everything is there, and it's just this sort of the long end where it's more difficult, or where it's more problematic. The delta you drop by could be actually very small, so it doesn't have to be a constant. It could be n to the minus something. If I followed the argument correctly, so.
Well, no. You mean you can take if you go back by delta over n, then you're losing a linear number of folds in length along the cycle. Because according to so in this statement of freeze, it's written non-decreasing, but it's more or less obvious that the function is increasing, which means if you step away from c to c minus delta, you are bound to lose a linear number of folds in the length of the longest cycle. It could be the case, and the second for our proof, on the other hand, we need a linear number of random edges in the second round of exposure, which means you are kind of trapped within these two things. Did I answer the question?
Okay, I maybe need to look at the numbers more carefully, but in the argument you had, the failure probability was quite large for short cycles, and then it just decayed off as e to the minus L times omega n. That's
true, but maybe you can take your delta to be slowly tending to 0, and then you can start comparing these two things. One of them slowly tends to infinity, the other slowly tends to 0, and maybe you can squeeze something out of. I'm not so sure.
So I was wondering whether you could get away with something slightly weaker than continuity from the Anastos and Freeze result.
Could be, but not sure you can squeeze much. You need to look into our proof and to see whether you can allow your delta to tend to 0.
Okay. Mm-hmm. Other questions? Thank you.
I guess it's the variant of Alex's question. I suppose one could look at the proof of Anastos and Freeze and see, does it allow, what flexibility it allows in the model? So, I mean, it can't require exactly GMC over n. It must apply to some GNP where p is close enough to c over n, but presumably just asymptotically c over n isn't good enough, otherwise you wouldn't have a gap. So I don't know whether you looked at that to see maybe their proof gives something, and it's conceivable that could fit with.
Well, you know, so
I think I'm saying the same thing as Alex, really.
Well, formally, and actually we did ask Alon about it. Formally, it does not follow from there proof that this function f is continuous. So theoretically, there might be a gap between it might be the case that C, as f is not left continuous at certain point C. It's really hard to believe. Because what they provide some basically an explicit way to complete f of C to any degree of precision. So if you give me C and if C is large enough, they can just compute C with a high and high degree of accuracy, but it's not a priori clear, or maybe even a posteriori clear that what you get is some a continuous function. So there might be a problem here. I mean, it's hard to believe, there's no reason in this world why this function f would not be continuous. It would be really extremely surprising, but somehow we are short-handed to prove.
Okay, any other questions? Okay, so this maybe is a good point for me to stop the recording and then to invite everyone to unmute